Hello everybody, how's everybody doing? CRS here. Almost everything expands on heating. If you have an object, when you raise its temperature, the length, the breadth, the height, almost every dimension increases in the same way. Now, when we look at what thermal expansion is, we can simplify it by talking about expansion in only one dimension at a given time. Of course, it can be spoken about in all the three dimensions later, but let's talk about what is linear expansion today. Dear friends, let's say that we have an object of length L. So here I have an object of length L. Let's write that the length is L. What we do next is we increase its temperature. When we increase its temperature by, let's say, delta T, something interesting happens. The object gets its length increased by a little bit. So the length of the object has now increased. If you ask me, CRS, how much length has increased? Before it was only this much, right? It was only this much. That was the length, but now it has increased by an amount delta L. That's the amount of increase that you see. Question is, what are the factors on which this delta L depends on? The increase in length delta L depends on the initial length, which is L. It also depends on the rise in temperature. Greater the rise in temperature, greater would be the change in length. So I shall write it as delta T. Let's combine the two proportionalities. We have delta L proportional to L into delta T. Let's make this an equation now. The change in length, my dear friends, the change in length is equal to alpha into L into delta T is all you will have. What is alpha? Alpha is a constant that we have put out there, and it's a constant for a material. For copper, there is an alpha. For aluminium, there is alpha. There's another alpha for aluminium. So different materials will have different values of the alpha. And how do you call alpha? You will have to name alpha now. It's called thermal coefficient of linear expansion. That's what alpha is called. The thermal coefficient of linear expansion. Let's make another equation which tells you what is the final length of the material when you heat it by an amount delta T. Well, it's quite evident that L dash and L are related by writing this way. You see, delta L is simply the new length minus the old length. Let's put it there. The new length L dash minus the old length, the initial length, is equal to alpha into L into delta T. Send that there. You have L dash equal to L plus alpha L into delta T. L can be pulled out as a common factor. You will have L into 1 plus alpha delta T. Well, this is the equation which relates the new length, the original length, the coefficient of linear expansion, the thermal coefficient of linear expansion, and the rise in temperature. L is the smaller length and L dash is the higher length. In that sense, this formula can be used. But anyway, going further, there are quite a lot of scientific instruments that work on this particular equation, on this particular principle, that when you increase the temperature, the dimension of the object increases. Example is a thermometer. When you increase the temperature, the volume of mercury inside thermometer increases. Just like in this case, the length is increasing, the volume increases. There are different materials. For example, there is a thermometer that measures measures temperature using a bimetallic strip. That's one of the points of discussion today, bimetallic strip. So bimetallic strips are used widely in various applications. They are used in iron boxes. They are used in different materials where you need to control temperature by various means. And there are other phenomena that occur and you want to measure the temperature. A bimetallic strip is used. So let's try and understand what a bimetallic strip is. So I've drawn it for you. Let's assume that here are two metals. The first metal out here, let's say, is copper. Let's say this is copper. So the coefficient of linear expansion, the thermal coefficient of linear expansion of copper, let's say, is alpha C. And the thermal coefficient of linear expansion of tungsten, let's assume that this is tungsten, is alpha T. Well, that is the situation. It's found that alpha C, which is copper expands more than tungsten when you increase the temperature by a little bit. So what happens as a result is that copper expands by a little more than tungsten does. This is welded in between, so they're not allowed to have they're not allowed to expand independently. So there is no other go but for this strip to bend like this. So you have a bimetallic strip bending. What we want to do today is to find the radius of curvature of this bimetallic strip. So look at this. This is the radius of the bimetallic strip. Okay, so this is the radius of the bimetallic strip. Let us assume that width of the bimetallic strip is W. On both of these widths are W. All right, that is W, and this is W as well. All right. So talking about where do you measure from, you start measuring from here. That's the center of the circle, for which these two form arcs. I would also like to tell you that we will be calling the radius of the first tungsten strip to be this distance, which is, you see, starting from here to half the width, and same goes with this one, right? So if you ask me, sir, what is the length of both of these? We will come to that. We will come to that in a while. But yeah, when you increase the temperature, what do you think is going to happen? When you increase the temperature, the length of copper wire, the copper strip, is going to be LC, and it's given by L naught into 1 plus alpha C into delta T. Now the question is, what is L naught? L naught is the initial length. L naught is the initial length. And similarly, when you increase the temperature by delta T, both of these strips will have their temperature increase. So the length of the tungsten strip would be equal to L naught. It's the same length. Initially, they start out with the same length. So we have 1 plus alpha T into delta T. So that's LC and LT. Well, we want to today find the radius of curvature, right? We want to find the radius of curvature of the bimetallic strip. So what you do right now is write these lengths, relating them to this angle and radius, let's say. It's quite an easy job to do. The angle made subtended by the bimetallic strip at the center, let's say, is theta. If that is the situation, and W is the width, you can say that this length is the length of copper strip, LC, on an average, and LC is simply equal to S equal to R theta equation. R is the radius. Radius is starting from here to here, that's the radius, but in addition to that, you will have to add a width as well, 1/2 of the width. So that's the total width, and you will have to take half of that because that's the radius. Starting from here to this point up to here is the radius of the arc subtended by the copper strip. So I shall write R plus W by 2 multiplied by theta. So that is LC, length of the arc equation. And similar thing can be done with the tungsten as well. LT would become equal to R starting from here to here. So the radius is from here to here. The W by 2 will have to be subtracted. This much will have to be subtracted. R minus W by 2 into theta. These are the two lengths. When that is the situation, you can just substitute for copper's length and tungsten's length from these two equations in here. Let's find out what happens. Well, the copper's length can be written as L naught into 1 plus alpha C into delta T equal to, on that side we have R plus W divided by 2 multiplied by theta, and then I'd like to divide both of them. Maybe we'll do that in the next step. We have L naught into 1 plus alpha t into delta t equal to R minus W divided by 2 multiplied by theta. I need to find the radius of curvature. So let me see. Let me get rid of as many variables here as possible, as many things as possible. So let's divide both of them. If you divide both of them, we have um, L naught into 1 plus alpha c into delta t divided by L naught into 1 plus alpha t into delta t equal to, taking the LCM, you have 2r plus w divided by 2r minus w. Of course, there is a theta on both up and down, so that gets cancelled, and L naught also gets cancelled. Let's continue. This is fun simplifying. 1 plus alpha c into delta t multiplied by 2r minus w equal to 1 2 yeah, so we have 1 plus alpha t into delta t multiplied by 2r plus w. Well, you simplify this. When you simplify this further, you are going to get, all right, let's simplify it, not a big deal. So we have 2r minus w, and then we have plus 2r into alpha c into delta t, and then minus w into alpha c delta t. That's the left hand side of the equation. The right hand side of the equation is going to look like this: 2r plus w plus 2r into alpha t delta t plus w into alpha t delta t. So this is the complete expansion. Do you see 2r and 2r would get cancelled? Let's look at this term and this term. Bring this here. It's going to be 2r, outside is a common factor. Alpha c minus alpha t is going to remain inside the brackets. There is a delta t also that comes out as a common factor. So I think we've taken care of these two terms. Let's send this w there. So you will have 2w there. It gets added up with that. And then plus w into alpha c plus alpha t multiplied by delta t is what you will have. Well, you can certainly pull w also as a common factor. You will have 2 times r multiplied by alpha c minus alpha t into delta t, becoming equal to w multiplied by 2 plus alpha c plus alpha t multiplied by delta t. Because alpha is very small, it's of the order of 10 to the power of minus 5. When the value of alpha is so small, you can simply neglect that. If you just neglect it, this term will go away. You can't neglect this, because if you neglect this, it's a product, it will cause a lot of things to go haywire. So only this can be neglected because it's being added with 2. Okay? That's the idea behind it. You can neglect this bit. If you neglect this bit, then because it's only 10 to the power of minus 5, it doesn't make any difference as such. R, my dear friends, then becomes equal to, on that side, it is W multiplied by 2, which is inside the brackets, divided by 2 times alpha c minus alpha t multiplied by delta t. 2 and 2 gets cancelled. When that is the situation, we have R, which is the radius of curvature, being equal to W divided by alpha c minus alpha t multiplied by delta t. This, my dear friends, is the expression for radius of curvature of a bimetallic strip. So here is the complete view of all the calculations we have done. The shortcut out here, I mean, of course, the formula out here can be considered a shortcut, and you can use it in any examination for that matter. But the questions on thermal expansion are very frequent in JEE Mains, JEE Advanced as well, CET, Neet, and all of these exams that you usually aim to score really well. So I need you to get this concept really nicely, and then this exercise calculating the radius of curvature will convey quite a lot of ideas for you to do things very quickly in the examination. Thank you so much.